All right, so proportion. We're going to take a look at soccer home team wins. So many believe that there's a home team advantage, and there's some data that supports that. So we're going to look at an example of that. So our population proportion, P, would be the proportion of home team wins. And a null hypothesis in this case could be something like, we think that, you're just, my camera's messed up. There we go. We're just as likely to get a home team win or not, in which case we would say the probability that the proportion of home team wins is 50%, right, 0.5. So that could be the null hypothesis. And there's a lot of people that believe that, no, the home team has an advantage. They're more likely to win. They have their fans cheering them on. So the alternative hypothesis would be that P is greater than 50%. Alternative notation for that, instead of writing out the words, you'll often see H with a subscript 0 and then a colon. The parameter, which is the proportion in this case, the null always has to have an equal in it somewhere, 50%. And the alternative is an H with an A or an H with a 1, could be a capital A or lowercase, doesn't matter. I usually use a capital, our book likes a lowercase, and this would be my alternative. And the alternative hypothesis can never have an equals in it. And the main reason is we can never prove something is absolutely a specific number because we never have all the data. So there's the null on the alternative hypothesis, and often we're given a significance level. So, and that relates to the idea of what it means to be a rare event. So I talked about the rare event rule before. So let's see, significance level is related to the rare event rule we talked about a while back, and probability. And the rare event rule says that if something has a 5% or less chance of happening, then it's rare. So that's what we're going to look at here. And that's the letter alpha. And typically we set that to be 5% is the typical rare event rule. If it's more life-threatening, then we might set it down to 1% or 0.5%. But 5% is kind of the default if it's just some issue we're looking at. So that's what I have there. Setting up a sketch of this, which you should always do. So if you email me a question about a homework assignment, I'm going to ask for your setup on the problem. And I'm going to ask you to send me a picture. And your picture should include a sketch that looks something like this. So we have a hypothesis test for proportion, home team wins. And the null hypothesis always goes in the middle, and the null hypothesis is that the population proportion is 50%. Okay? And the alternative determines what type of test we're going to run. So my alternative hypothesis, HA, that's P is greater than 50%, right? We think the home team does have an advantage as the alternative. Since that's a greater than points to the right, so this is a right tail test. And if you get the type of test wrong, right tail, left tail, two tail, then that totally screws up the test. It just doesn't work. So the next thing I would mark in here is, since it's a right tail test, I would put a mark over here. And this over here is what alpha is, and that's the 5% is going to go in the tail. And what alpha does is it basically draws a line in the sand. It says if your data ends up over here, so if my P prime is over here, then that's close to 50%. which means the home team doesn't seem to have an advantage. If, however, the data ends up out here, P prime would be from the sample, then this is far from, this region is the line in the sand that says that's what far away means. So that's far from 50%, which implies a home team advantage. And the reason that is we assume that the home team doesn't have an advantage, which means they're just as likely to win or not win. Based on that assumption, we found that we got a sample that's unusually rare. And, you know, rare things just, you know, they don't happen to most people. So either the sample is bad or the assumption that it was 50% is bad. So that's the reason we say, oh, we're going to reject the 50% because this shouldn't have been that rare, right? This happens all the time if it's a good sample. So that's kind of the reasoning here. So that would imply a rejection of the null hypothesis and then an acceptance of the alternative hypothesis. And that doesn't mean that, you know, we know exactly what the home team advantage is in terms of a percentage. It just means that we believe it's bigger than 50%, right? So that acceptance really means we have evidence. That didn't go well. Evidence that P is greater than 50% is what it tells us. So we'll see what happens. You know, we might find evidence, we might not. All right, so let's run the test. So this is my initial setup there. So then I go to StatKey, and if it's their data, I just make sure I have the right data set. I make sure I have the null hypothesis set correctly. I make sure my sample data is set correctly. So their particular sample, out of 120 home games, 70 of those home games, the home team won, which is a proportion of 58.3%. So the question is 58.3% kind of close to 50%, or is it far enough away from 50% to say, oh yeah, that looks like a home team advantage? Okay. And you know, how do you draw that line in the sand? And that's again what a hypothesis test tries to do. So then we start running the simulator, and what that does is it makes a deck of cards, 120 cards, 70 times the home team won, and the other 50 times the home team did not win. It then redraws the card, and so each time you get a slightly different sample, 59 out of 120. Over here, we got a 45 out of 120. Over here, we got a, oh my gosh, the home team won 85 out of 120 times. So it's all over the place. What kind of test are we running? Again, we got to look back at the situation. And the situation is based on the alternative hypothesis as far as which test, and the greater than implies that we do a right tail test, because greater than means you're to the right. So we choose a right tail test from here. All right, so the next thing we look at is the p-value. So once we get the test started here, we're not done, that StatKey just randomly puts a 2.5% in the tail. We look at the data here and we enter our proportion on the x-axis. So down here, I enter 0.583, which is the sample data, and I'll draw a sketch of what I'm doing here too in a sec. All right, so what this says right here, assuming that the home team doesn't have an advantage, that they have a 50% chance of winning, finding a sample of 58.3% of wins, there is about a 4% chance of that happening. Okay. So is 4% fit the rare event rule? And the line in the sand we drew was, if the probability was less than 5%, then we would say, yeah, that's weird. Okay, something's wrong with the null hypothesis then. So we have sufficient evidence to reject the null in this case because my p-value is relatively small. And again, that's kind of a judgment call one makes. So often in modern hypothesis tests, people don't actually state often their significance level of 5%. What they do is they just state their p-value and they leave it up to the audience to say whether they think that p-value is small enough to warrant evidence of the alternative. All right, so let's go to a new page. And I'm gonna I can just draw over this picture here. So that was my alpha right there. I'm gonna redraw with, let's say, is yellow viewable here? Right around here. So if this marks 5% of samples in the tail, then if I put a mark right there, then this over here should be 4%. That's kind of hard to read. Or actually the computer said it was 3.9%. Let's make that a little more accurate. 3.9%. This number representing the tail probability, that's what we call the p-value. And I found the p-value by plugging in my sample data. And I'm going to switch to red. So this x-axis value here was my p prime from the sample. That was 70 over 120, which was 0.583. So again, to find a p-value, you got to run a bunch of simulations to get a distribution. And then once you have that distribution, make sure you have the null hypothesis in the middle, right? Then on the x-axis, we plug in our sample data, and then we look to see what probability the computer says goes with the sample data, given that the null is in the middle. So I'll write out in words what that p-value is, but I just want to show you in StatKey again. And I'll redraw that for clarity and state the decision and the conclusion. So the decision is just, do you reject the null or do you fail to reject? And then the conclusion is kind of explaining to me and my mom what it means. So again, in StatKey, I have to make sure I have the right null, which was 50%. Then I take my sample proportion, the 0.583, and I plug that in on the x-axis. Then the resulting number up here is the probability that the percent of samples, other samples that had a higher home team win percentage than 58.3. Okay. So assuming that the home team doesn't have an advantage, there's a 3.9% chance we'll find other samples of 120 home games where the home team won more than 58.3% of the time. I know that's a mouthful, but that's a conditional probability that we were talking about a couple weeks ago. All right, so new page, let's write that out. So I'm going to redraw the picture. Oops, wrong button. Come on, that button, come here button, there. All right, so again, switch colors. We have a hypothesis test, proportion of home team wins, and we draw our smoothed out distribution, which almost always has a bell shape to it because it is a distribution of sample proportions. So this picture is a distribution of sample proportions. Let's see, yours said 3.7. Yeah, I just saw the text up there. Yeah, so because we're running a simulation, every time you run it, it's going to be a little bit different because again, it's drawing decks, you know, a deck of cards thousands and thousands of times. So if I do mine again, just for fun, so I'm going to reset my plot, start over. Again, when we do this, we got to make sure of a couple things. Are we doing a mean or a proportion? This is a proportion. Is the null hypothesis set correctly? Is my sample data entered in for the count and the sample size? And this one came with a 70 and a 120, I'm just using their data. And then once I'm sure of my null hypothesis and my data is set correctly, then I start running thousands and thousands of samples. And remember, we do at least 6,000. You can always do much more, you know, for fun. Let's do 10,000 today. And then you get to decide which test you're doing. My alternative was a right, so it's a right tail test. My alternative was greater than, sorry, right tail. And then once we choose the test, we plug in our sample data, which was the 58.3%, so 0.583, and I'll probably get a slightly different number than before. I got 4.1% this time. So these are going to vary every time you do it, and I tried to set up the online homework so it took into account that slight variation, but every once in a while someone's going to get a simulation that defies what I thought was possible. If you think you did it right and you're close enough, just message your instructor and I'll take a look and let you know. So this time I got 4.1, Charlotte got 3.7. but they're in the ballpark. So what I want to do is draw this p-value picture here. There we go. All right. So whenever we do one of these, we have to label the center, and the center always comes from the null hypothesis. So that was p equals 0.5. Then you decide, is it a right tail or two tail? I'll do a two tail test soon. So over here, we're going to make a mark, and we're going to put p prime. My p prime was, oops. Since that's a decimal, I should put this at a decimal, 0.583. And again, that's just the proportion of home team wins from the sample. That's that 70 over 120. And then what I really want to know is the percent of other samples that are bigger than mine here. And the computer said that was, somewhere between 3.7%, 4.1%. So I'm going to go for the 4.1% this time. So that right there is 4.1%, which as a decimal is 0.041. And that right there is what we call a p-value. Now, this p-value is smaller than the 5% cutoff rule, which is the default I'm going with here. So what that means is my decision should be to reject the null hypothesis because I have a small p. Reject null. And then my conclusion is kind of, what does it mean to reject the null in this case? And that's kind of to me and my mom. So the conclusion here is we have sufficient evidence. It's usually the way it goes. That the proportion, and again, there's tons of different ways to word these, of home team wins is greater than 50%. Okay, so that's one way I could word it. And again, there's a bunch of others. What does the p-value mean? That's a whole nother thing, kind of different from the decision and the conclusion. So this is something I want you to know about. So I'm going to explain the p-value in this situation next. I'm going to put that on a new page. So in probability notation, p-value is the probability, capital P for probability, that your sample proportion is, let's see, greater than whatever the sample was. In this case, that was the 0.583, given that we were expecting the proportion to be 50%, the null hypothesis. Oh. And so as far as that goes, this right here means getting another sample that's more extreme. So more extreme in this case would be bigger, sometimes it's smaller, than the current sample. Oops, than the current sample. And this part over here is given the null hypothesis is true. So if we get a very small percent, so if p is small, that means either I have a weird or bad sample, or the null hypothesis really isn't true. And we usually say, no, this is a really good representative sample. That means there's something wrong with the null hypothesis. This shouldn't be a rare event. This is evidence that this is a common occurrence. Okay. So in words, this p-value is the probability of finding another random sample with a proportion of home team wins greater than that 58.3% when we were expecting the null. And what does the null mean? 50%. When we were expecting a proportion of 50%. And again, we found in this case that was about 4.1%, depending on which simulation you go with, 3.7, 3.9, somewhere in there. That's less than 5%, which is unusual. And if something is unusual, that means we have to question why is it unusual. And the main two options here are either my sample is not a good one. Let's assume the sample is a good one. So that means the null hypothesis must be the problem. That assumption that it should have been 50% must be incorrect. And this data supports that it's greater than 50. That's what all of this is telling us. Oof, that was a mouthful. Let me get a sip of water. All right, so let's see. What else did I want to do? Does anybody have a homework request? I had a few. Two-tail test is one I haven't done yet. I did a left tail test yesterday about human body temperature being less than 98.6. This was a right tail test because we thought the proportion of home team wins should be greater than 50%. And you got to read the fine print on the problems. Okay, let's see who else joined us. I heard a ding dong, I thought 12 or 13. Okay, I was wanting to do one of those yesterday. Let's see, I can't tell if I have any more people. I don't think so.
No, I left and came back because I had signal issues.
Okay. Thanks, Michael. Appreciate the notification. All right, so let's take a look at 12 or 13. I'm gonna go for 13. Usually, the bigger the number, the harder they are. All right, so let's see. Test the claim that the average heart rate of ICU patients is at most 95 beats per minute. Remember, anytime we get a claim, the claim could be the null hypothesis, and it could be the alternative hypothesis. We got to kind of figure that out. And how do we decide the difference between them? And the decision is, does it have an equals in the claim or not? If there's an equals, it has to be related to the null. If there's no equal sign in it, it has to be not the null. All right, so let me see. I am going to steal that text and start playing around with it in my notebook. So I highly recommend you write this down on paper. Try and figure what the heck is going on, because I can't do it without writing it on paper. All right, so there's my claim. Let's move you. Actually, I'm gonna stop this recording and start a new one. Let's do that real quick.